Thanks very much, Andy, and thanks to everybody for coming this morning. It's great to see so many of you here. Can everybody hear me okay? Yep. Okay, so this morning I'm actually delivering this presentation really on behalf of our partners and friends in the science and technical agencies of the Government of the Philippines, and some of their logos you can see there, as well as on behalf of colleagues here at Geoscience Australia and our partners over at the Australian Aid Program, without whose support none of this work would actually happen. Okay, so I know we're only at 11 o'clock and we are approaching lunchtime, and I don't know about you, but that looks like a pretty good lunchtime meal to me. We don't often think about how a meal was made when we're actually sitting down to consume it, but I just want you to consider the following for a moment. You're a chef, and your task has been to work with a group of new chefs. And you've been asked to prepare a meal for a bunch of customers, but there's a few catches. Your customers are very, very hungry, but also the chefs are hungry, and they also want to partake in the meal. There is no recipe. You don't know what the recipe is, and your chefs are asking for you to help them to create one. You have no picture of what the meal's actually going to look like at the end. To do the cooking, you're going to be doing it in multiple sessions. You can't just do one shot at it in the kitchen. And by the way, there's going to be different kitchens that you're going to have to move to from session to session. Each kitchen is going to have its own unique set of implements. Some that you really need are going to be present and some are not. And sometimes you might have to actually build your own implements to do the preparation. You don't know what ingredients are going to be available from the beginning. That only emerges over time. Every time you have a session, new chefs turn up and they have to be brought along for the experience. And all of the consumers are using a different set of crockery and cutlery, and you've got to keep that in mind when you're preparing the dish. So, how do you think you'd go? Just keep pondering that. You might be wondering at this point, what's he talking about cooking for? We're here for a lecture on disasters, aren't we? We'll get back to that. You might also be wondering why Geoscience Australia is concerning itself with disasters in the Philippines. Surely we've got enough of our own to worry about. And well, yes, we do. But GA has had a long history of providing advice and information to government on hazards and their impacts for many years. So when we talk about natural hazards, we're talking about the geological and hydrometeorological events that might come on suddenly or might have a very slow onset. And so these hazards events affect people because they have an impact on our communities, our livelihoods, and it costs a lot of money to continue to just merely respond to those disasters every time they happen. Much better to actually invest up front in mitigation and activities to build resilience. But to make those decisions around mitigation and resilience, we need some evidence. The evidence to make those decisions is a risk assessment, and at the core of a risk assessment is a risk analysis. So when we talk about the impact from a natural hazard, we're talking about what one event might do to the things that we value: people, our homes, our businesses, our services, our food production, etc. Then when we talk about risk, we're talking about the likelihood of a whole range of credible events that might happen over time and the accumulation of the effects of those events. So how do we do that? Well, we do that by combining information about hazard, exposure and vulnerability in a computational environment. So that's really about subjecting elements that are at risk to a hazard and then calculating how they might behave using models of vulnerability. From there we can calculate the direct impacts, such as damage, the economic loss that might be experienced, or the sorts of casualties that might be inflicted. But we can also look at the indirect impacts, the downstream effects that those impacts have. So you could think of risk analysis as being the who, the what, the where, and the how of disasters. Now there's a truism in all of this, that everything happens somewhere at some point in time. And so for that reason, the work to develop hazard models and exposure information has geospatial concepts at its very core. And today we're going to focus on that, the where and the what, specifically for the elements at risk. So to understand exposure, we need to locate and characterise elements at risk. So the location of an element at risk, such as the building that's been circled here, can be represented as a point on the Earth's surface. It might have some geometry around it, but it certainly would have some reference to the Earth. And location also can be an attribute about what it belongs to. In this case, maybe a geographic or administrative region. Now, if we were just doing mapping for the sake of displaying, we'd pretty much stop there, but we might give that building some sort of label or name. But because we want to characterise how that building might be impacted, we need to add some further information. So we need to actually add information that's going to have sufficient detail to enable us to relate that element at risk to the models of vulnerability, and so that we can understand the impacts from an engineering and economic and social point of view. So Geoscience Australia has been applying geospatial information capabilities for several years to tell the story of impacts and risks from natural hazards. And the application of GIS has been at the core of this work. This all started in the late 1990s with the Cities project, where selected cities were studied, and the impacts of natural hazards were understood, and information was built up by bringing together the geospatial data of hazards and exposure. Now, from the early 2000s, Geoscience Australia responded to a call to close nationwide gaps on information to help mitigate against disasters. And as a result of that, the National Exposure Information System was born. It started off life as a statistical representation of residential buildings and population, and relied very heavily on census data to do that. It's since grown to incorporate actual data sets from Commonwealth, as well as state and territory governments. And here you can see an example of how the building locations appear in Nexus. Nexus also stores the characteristics that are needed to interact with those models of vulnerability that I mentioned. So here for a residential building, and then again for an industrial building. So while it's true that Australia has its fair share of challenges with natural hazards, for our neighbours to the north, natural disasters represent a major threat to lives, livelihood and economic prosperity. Years of progress can be wiped out with a single event. And that can return people to poverty who might have climbed out of poverty, or actually keep people in poverty. So reduction of risk from natural disasters has been a key pillar of the Australian aid program for a number of years. And through the support of the program, Geoscience Australia has been partnering with national governments in the Asia Pacific region to enhance the capacity in those countries to understand the impacts and the risks. So this aid work's very different to the sort of aid that you might see on TV. In this work, there's no tent cities, no bags of relief goods or boots on the ground. And so due to its tectonic setting and its location in the tropics, the Philippines is prone to a variety of hazards. And coupled with the high population and recent economic growth, it consistently rates as one of the highest at-risk countries in the world. And in 2006, the former AusAid supported GA to assist the government of the Philippines in the response to a fairly major landslide that killed over 1,000 people. And what followed from that support was an invitation to work with the science and technical agencies in the government of the Philippines to look at enhancing the risk assessment capacity. And so that started with a 3-year program looking at multiple hazards, and resulted in a key set of recommendations to the government of the Philippines. One of the projects that was undertaken in that work was a pilot earthquake impact study for a place called Iloilo, which is virtually in the centre of the geographic centre of the Philippines and has a population of about 500,000 people. And so that work brought together existing hazard models together with new data on buildings and population and newly developed vulnerability models, engineering vulnerability models developed within the Philippines. And so the aim was to bring a quantitative impact assessment capability to an existing earthquake damage assessment tool that partners in the Philippine Institute of Volcanology and Seismology, or PHIVOLCS, have been developing. And so that work started in 2009, but about a third of the way into the study, the passage of a typhoon through the north of the Philippines would lead to a new opportunity to build up further risk analysis capacity in the Philippines. So Typhoon Ondoy passed over central Luzon in September 2009, and while it did generate strong winds, its most lethal element was the heavy rain that it delivered to the catchments of the Pasig Marikina River, and those catchments to the east of the area which is known as the Greater Metro Manila area. So a very large flood event ensued, causing hundreds of deaths, hundreds of thousands of displacements, and large areas of the city were inundated, some for hours, some for a few days, but there were some areas that were still inundated months later. And so at the time, the former AusAid in Manila asked Geoscience Australia if something could be done to look at the impacts from these sorts of events, to provide evidence on how to mitigate against them. And Geoscience Australia said yes. And so building on the existing relationship that we had with the science and technical agencies, the existing program of work was augmented and upscaled so that we undertook a risk analysis within the Greater Metro Manila area. So it was called, AusAid had a name for it. Our Filipino colleagues gave it the name GMMA Risk Analysis Project, or GMMA RAP, or RAP for short. Commenced in 2003 2010 with a 3-year duration, and it had these 6 components. The very first component was the collection and management of high-resolution digital elevation data, and this was going to provide the foundation for the remainder of the technical activities in the program. And the brief was to cover all of Metro Manila and parts of Rizal Province, which sits just to the east of Metro Manila. So let's talk a bit about GMMA. Greater Metro Manila area, or GMMA, is 16 cities and 1 municipality of what is known as Metro Manila, plus the urban areas to the north, south and east. Today it is a megacity, and depending on where you draw the line, has a population of between 15 and 25 million people. It's the political, financial and industrial hub of the country. It has the largest maritime port and the main international airport. It has numerous business and industrial precincts, and is home to many government and academic institutions. So this is the extent of the project area that we were going to be working on. But in actual fact, the real urban footprint of the Greater Metro Manila area extends well beyond that. By way of comparison, this is the urban footprint for Canberra. Canberra has a population of about 400,000 people. The population within that yellow area is around about 13 million, so you get a sense of the scale of the problem. GMMA is a very complex urban landscape, unlike anything we see in Australia. The Philippines economy is growing very strong. It's powering ahead, and the Metro Manila area is growing rapidly. More multinational companies keep setting up operations out of the Philippines, and as those operations continue to grow, there's more employment, more people wanting to move to the city to take up those opportunities. Manila is a very important city for Australia. If any of you have tried to call your phone company or bank recently, it's pretty likely you're actually speaking to somebody who's working out of Manila. So the newfound prosperity means that there are more people on the move, resulting in a lot of congestion, air pollution and noise pollution. And the rapid urban development is putting a lot of pressure on existing infrastructure. And there's a desperate need for new infrastructure in many areas. Once productive land on the fringes of the city are now being consumed by housing or industrial estates, and there's even some reclamation of land into Manila Bay to the west. So while there is growing wealth in the greater Metro Manila area, there's also a very large population of low-income families, and informal settlements have sprung up around the city, and these settlements contain homes that are made from improvised materials or very low cost or substandard materials. And so you can see in those cross sections there, there's actually a lot of, there's not much distance between the wealthy people and the not very wealthy people. These settlements are very opportunistic. They're often in vacant or idle land, restricted or dangerous areas alongside of waterways or sometimes on contaminated land. And the people that live within them are perhaps some of the most vulnerable in the Philippines. So natural hazards are also a very real threat to the greater Metro Manila area. So we saw some of the flooding earlier, and that's in large part because Manila is set in an alluvial floodplain between Manila Bay and a freshwater bay called Laguna Bay to the east. It's also built on an active fault which has generated large earthquakes in the past. And we can see those circles on the plaque out the front of the cathedral in Manila, which has actually been destroyed at least 3 times by earthquakes in the past. So typhoons can pass over or near the metropolitan area, and they can generate storm surges off the bay as well as generating lots of wind and rain. Out to the west is the Philippines Trench, the Manila Trench, which is capable of generating a tsunami which might run up into Manila Bay and affect the metropolitan area. And to top it all off, there's an active volcano to the north and the south of the city. So there's something for everybody there in terms of hazards. So our work was not actually the first time that an attempt had been made to quantify the impacts from the hazards. In 2002, a project between the Japanese government and the Philippine Institute of Volcanology and Seismology and the Metro Manila Development Authority was conducted, and it was called the Metro Manila Earthquake Impact Reduction Study, and it, as it implies, looked at trying to understand the potential impacts from earthquakes. So it used quite a lot of geospatial data to try to capture the complexity of the urban environment. And while some attempt was made to characterise the buildings in Metro Manila, it did not classify them in a way that could be integrated with vulnerability models in a really easy way. There are some other aspects about the work that meant that it could not be easily repeated. And it only covered the 17 cities and municipalities of the Metro Manila area. It didn't actually go to the north and south where development actually occurred. So one of the objectives of the project that we had with the Government of the Philippines was to improve on that work, especially on the development of exposure information. So with the pilot earthquake impact study, some work was done to survey some of the building stock in the city to try to understand the relationships between statistical information about the building stock and what was actually there. And so the intention of this was to include an exposure module inside a tool that PHEVOLCS had actually developed themselves called the Rapid Earthquake Damage Assessment System, or REDAS. So this is a homegrown piece of software that can be deployed onto a laptop. And so the first phase of the survey work was done using ArcPad software and some devices that we brought along. We returned for a second survey about 4 months later, and by that time PHEVOLCS had actually adapted what was in that mobile GIS device and actually embedded it in the REDAS software. And you can see there how they're testing the image capture part of that. So through that work, around about 1,000 buildings were surveyed, and we saw a very diverse mix of land and building uses in the areas that were surveyed. There's very little homogeneity in the use of buildings in Iloilo. So at the beginning of the project, FEVOX nominated themselves to lead the exposure information development based on the great work that they'd done in Iloilo. And they were very keen to try to teach local governments and other partners to capture data in that exposure module in their REDAS software. But from the Iloilo work, we realised that it takes around about 12 minutes for somebody to approach a building, have a look at it, recognise the characteristics on the facade of the building, enter the data into whatever survey module they're working with, and take a photo and move on. So the question then came, well, can we really capture data for every building in Metro Manila? So we did a back of the envelope calculation, and we realised that within the time that we had available to actually do the data development, we would need at least 105 people working full-time capturing data across the city. So when we think about all the things that make surveys difficult and uncomfortable in a busy urban tropical environment, we realise that we're actually not going to have a very good time. It's an expensive exercise, it could be a logistical nightmare, and really it's quite unsustainable as well. So how are we going to characterise the urban environment in Metro Manila? So we needed to turn it around, take a different approach, and we talked to FEVOX about what Nexus was and how Nexus philosophy could be adapted to the Philippine setting. And the key to all this is that building and maintaining an integrated, centralised and spatially enabled database is the most effective way to manage exposure information. And it's the most sustainable way to do it as well. And it would require a lot of ingredients, a lot of spatial data to locate the elements at risk and then to characterise them. So this is not a very easy concept to explain to people whose practices wouldn't normally jump to thinking about how to combine data that might, on first look, seem quite disparate. So how do we explain this? Well, food is very, very important in Filipino culture. In all of the activities that we had with our partners in the Philippines, food always made an appearance at meetings, even if it was a short one. They talk about problems in terms of food. If something is too massive or too complicated for them to take on, the saying is, oh, that's too far from the stomach. So well, we thought, why don't we talk about this in terms of cooking? So what do you do in cooking? Well, you choose a recipe. You gather ingredients that you're going to need to prepare the meal. You go to the kitchen and you get all your implements together. You organise your ingredients, and you might just chop some raw ingredients up and that's enough, but other things you might actually have to prepare and mix up. Then you add all that to the pot or to the fry pan, and then you boil and you fry and you simmer, and then you adjust it to taste as you go to make sure you get the flavour right. And then when it's ready, you notify your diners and you serve it up. So data integration is very much like cooking. You need to select a method by which you're going to actually integrate the data. You need to acquire the data from somewhere, either capturing it yourself or using somebody else's data. You need to create a working environment in which you can bring all these ingredients together. You need to gather and acquire and manage all of the tools that you're going to use. Manage the data in a sensible and logical way. Reorganise the data if you need to, and then prepare the data for the integration. Do the integration, process it, monitor the quality as you go, and then when it's ready, you report on it, and then you make it available for dissemination. So we found this was a useful way of talking about data integration to our Philippines partners. So what were we going to capture in the exposure information in Metro Manila? Buildings and population were the primary elements at risk, but we also had a brief to look at the potentially wind-sensitive structures, such as the very massive billboards that like the one that you see there. And so this work started with one motivated local government, and then the concepts built with that government would then be transmitted to the rest of the project area. But we had to do what surveyors do and think about it from the whole to the part. So the first thing we needed to consider was the administrative geography of the Philippines. And so you can see the hierarchy of how administrative and political areas are managed in the Philippines. The smallest administrative and political unit in the Philippines is a barangay, which is around about the equivalent of a suburb in Australia. But some barangays can be as small as a few city blocks, but some can be as large as several Australian suburbs. And much of the official data available from governments in the Philippines is available at the barangay level. There are about 1,060 of those barangays in the project area. You might be able to just make out some of the boundaries of those there. We had several problems in handling that data. There are lots of boundary disputes, either within the local governments themselves or between local governments. And some of these have been unresolved for decades, leading to great uncertainty about where the boundaries actually sit. So our problem was that some of those boundaries don't follow natural features. They might have been drawn up through some arbitrary agreement years ago, and development does not always honour those boundaries. There's also no authoritative source of boundary data. Even within local governments, there can be different understandings of where those boundaries are. So we had to deal with that problem because a lot of the data that we were hoping to use in the integration process was attributed to the barangay level. And so we had to use different versions with different data sets to try to paintbrush that information. So earlier in the discussion, I talked about the complexity of the urban environment and how do we capture that. So land use mapping is one way of doing this. Early on in the work, the approach was to think about a barangay and just try to think about its dominant land use, whether it was residential, commercial, something like that. But because of the complexity of the urban environment, it's not really possible to do that and meaningfully characterise the buildings and the distribution of the population. So we had to start working with land use mapping. And it's not the first time that land use mapping was done. This is an example of some of the land use mapping that came out of the earlier study between FIVOX and the Japanese. But when we placed that mapping over some more contemporary imagery, we can start to see that the accuracy of that mapping needs to be looked at. And we can see some developments, new developments that didn't appear in the mapping, and also some offsets from existing development that not quite in its right place. So we needed to work to update and upgrade that data. And so one of the first things we needed to do in that work was to actually come up with a land use classification schema that was going to work for risk analysis. And so we worked with the partners to come up with the variety of uses that were found throughout the metropolitan areas. And we made the distinction that this land use mapping was very different to the type of land use mapping that, say, city planners might think about in terms of what is a prescriptive land use, what you're actually permitted to do in a particular area. And so what we did was we came up with a hierarchical classification system which had 5 levels of detail, enough to capture the complexity of the urban environment. And it incorporated categories for those sorts of facilities that the Philippines government would regard as important for disasters. So it was a pretty daunting prospect to try and map the whole city like this with around about, I think it was about 60 categories. But fortunately, we started receiving existing mapping that helped us to very rapidly turn into land use data. So we were provided with some data on the extent of road corridors and waterways, and we were able to actually invert that to then derive areas of land where activities were occurring. So then the work was done to categorise each of those polygons and record some other attributes like the name. So our partners don't actually have access to the same proprietary software that we have in Geoscience Australia. But that was no problem because we picked up on the ever-evolving and maturing QGIS, free and open source GIS software. And it wasn't long before FEVOX had actually deployed QGIS to every one of their laptops in their agency. And then what happened was that FEVOX actually invited local governments to come and participate in the land use mapping because local knowledge is the best piece of evidence for attributing the land use. So over the next 18 months, land use mapping was performed for 24 local government units. And so the local knowledge plus other data that arrived was the evidence that was used to put a classification on each of those 85,000 polygons or thereabouts. And so staff from the planning office and the disaster management office and also the city assessor's office, which is the equivalent of the Valuer General in Australia, those people provided a lot of really valuable input. And the result was the most up-to-date land use mapping for anywhere in Manila, and the combined result is shown there. So one of the drivers of vulnerability for buildings is the construction practice, and that is how the structural system is assembled and the non-structural elements that are attached to the building. So in the Philippines, the National Building Code of the Philippines was introduced in 1972, and that was the first time that some standards were inserted around strengthening buildings against hazards. And then there was another major change to the thing that followed, so that which is the Structural Code of the Philippines in 1992. So the vulnerability models that were going to be developed for the buildings in the Philippines would also take into account the age of the building. And so what we needed to do as part of the exposure information development was to capture what we call the era of construction. So there's 3 eras there. How are we going to do that? Could we do it through administrative data? Well, yes, maybe, but is there sufficient data captured by local governments and national governments on building age? Maybe, maybe not. There is some historical aerial imagery that we were able to refer to in the holdings of the Philippines government, but not the full coverage of Metro Manila and not at the dates that we actually needed. But fortunately, Geoscience Australia was able to access the archive of Landsat imagery over the Philippines through some work it was doing through the International Forest Carbon Initiative. And what you actually see here on the right is some satellite imagery from 1972 and from 1996, which is about the best proxy that we had for the 1992 threshold. So in an activity that was conducted here in Geoscience Australia when our Philippine partners visited for a technical activity, we used the ILWIS free remote sensing analysis software to train the software to classify the image and then refer back to some of the historical aerial photos that we had access to try and see which classes translated to urban development. And then for each of the images we had an output data set that shows essentially the urban footprint at that time. Then we combine that together to create this map of era of construction. And unfortunately this is one of the ones that should be coming through on the red channel, but red channel's absent. So, but what it does show is a development trend outwards from the what's essentially the core of Manila, which is the old part of the city, sort of towards the centre and the left there. It wasn't enough just to accept the results of the classification from satellite imagery, so again we relied on local knowledge to try to validate that data. Now, as I mentioned earlier, there's a lot of buildings in Manila, around about 1.6 million buildings in Metro Manila alone, let alone how many buildings out to the east and north and south. And so one of the data sets that arrived early on was a building footprint data set. But we had a look at that and we found that it was ageing quite considerably. It captured some areas really well, but then there was a lot of new development where buildings weren't present. And the way that the buildings had been captured in that data set was not really going to help us with including in the exposure database. There's also a lot of interest in the Philippines to understand what the count of buildings are, the number of buildings that are going to be affected in different ways by the different hazards. But damage calculations in an impact and risk assessment is done using building floor area. So we had a challenge to try to quantify the building floor area in Metro Manila. So could we just take a building footprint and assign a height to the centre of that and try and derive floor area of that building? Well, not really. And the reason for that is that a lot of buildings have what we call vertical irregularity. So they might be wide at the lower levels, but then take on a different shape as they go up. And so you can't assume that a building's just going to occupy a simple volume. So our challenge was, how could we rapidly estimate the floor area of buildings in this megacity? So you might recall in the first part of the program, there was a mission to capture the high resolution elevation data. And this was performed using LiDAR technology, which blanketed the surface of the Greater Metro Manila area with laser measurements from an aircraft, which resulted in billions of points of data containing the horizontal coordinates plus the height above sea level of the very first surface that laser reflects off. And that first surface could be anything from open ground to road surface to the tops of trees to the tops of buildings. So our component wasn't able to deal with that volume of point data very well, but instead we decided to work with the derivatives of that survey, which are the digital surface model and the digital elevation model. So the surface model is a grid data set, 1 metre resolution across the project area, indicating the height above sea level of those first surfaces. The digital elevation model attempted to remove the surface effects and provide what we call a bare earth model. So when you've got the bare earth model and the surface model, you can actually subtract the two and get the height above the ground. So the building tops were an obvious feature in the surface model, but how can we isolate the buildings in the surface model? We can do that, and this is a part of the Greater Metro Manila area where the subtraction of the surface and the terrain data has been done. And so we can see the heights across the different buildings there. The buildings off to the left of the screen there are generally fairly low-rise buildings, but then towards the centre there are some more high-rise buildings. Unfortunately, the colour's not coming through particularly well. So what we had to do is to try and come up with a way to erase everything from that's not a building. So some of our earlier land use mapping allowed us to do that in the road corridors, so we can remove the effect of bridges and trucks and other surface features coming through. We had other data on some other structural elements like large water towers, etc., so we could mask them out. But how are we going to mask the vegetation out? Well, fortunately, the aerial imagery that was captured at the same time as the LiDAR was captured in 4 bands, colour plus infrared. And this allowed us to apply a process to get what we call the Normalised Difference Vegetation Index, or NDVI, and it's a measure of vegetation health. So when we do that with that imagery, that's the extent of vegetation at various heights. So then we can actually use that as a mask to remove surface features where there's vegetation. And we're left with the heights just across the tops of the buildings. So that's great, but how can we calculate floor area from that? So in modern Australian homes, you'll find that the ceiling is around about 2.4 metres above the floor. In this building, the ceilings are closer to 3 metres, but the height to the next floor is about 3.5 metres. And we call that height, that second height, the inter-storey height. And different buildings have different usages and need different ceiling heights. So they then have different inter-storey heights. So this is where we had a light bulb moment. We'd already mapped the land use. We'd already been able to calculate the height of the tops of the buildings. We could obtain some data on the inter-storey heights for different buildings and the different land uses that we had, and then determine where that height sits within the height of the top of the roof, how that sits with the inter-storey height ranges for that particular land use. And so what the result of that is for each grid cell is the height at that part of the building expressed as a number of stories. And because each of those cells are 1 square metre, we then actually have the floor area at each of those cells. So that's great. On its own, still doesn't help us that much, but when we draw a polygon around a group of buildings, we're then able to calculate the sum of the floor area. And this is an example of how the heights had been categorised once we do that conversion from the inter-storey heights. So that process has many steps in it, and at the Geoscience Australia end we constructed a process to string them all together. But we needed to do something to make that process easy for our Philippine partners to run. And so what we did was to combine all of those processes in the Python programming environment, which accesses ArcGIS software to do those calculations, but it doesn't require the user to actually be in ArcGIS to actually do it. A graphic user interface was developed to allow somebody to easily input all of the data sets and then produce a result that then they can then visualise in any GIS package they wish. And so we called this the building geometry model, and it enables users to easily calculate floor area. It also has other byproducts that might be useful. This was released as an open source software product here at Geoscience Australia. It's available for download off the website. We also provided some training to partners, and we use this to great effect. We could calculate and estimate building floor area in the Greater Metro Manila area in a matter of hours. So our next challenge in all this work was to try and characterise the buildings in terms of their structural characteristics. So what we needed to do was to try to estimate the quantity of building floor area according to a building classification schema that was developed by the University of Philippines and their Civil Engineering Institute. So that's the classification schema there. Essentially breaks buildings down into 4 main categories, predominantly wood, masonry, concrete and timber. But then it goes into more detailed classifications and then also includes some thinking about the height of the building and the age of the building. So there's about 20 types and 42 subtypes within that schema. And so here we had an opportunity to augment some of the work that we'd done earlier in Iloilo, and the best and most consistent data available for the residential building stock was data from the Census of Population and Housing, in which they asked the householders questions about the roof and wall type of the building. And it's possible to combine those two and look for the relationships between those combinations and the schema that I mentioned before. But there's not a one-to-one match. There's a lot of intricacies in the relationships. So for the non-residential building stock, we were hoping that the local governments would be able to provide a lot of data about the commercial, industrial, institutional buildings. And so our best hope was to access data from the assessor's office from each of the cities. So as I mentioned before, the assessor's office is a little bit like the Valuer General in our states and territories, and they record data about buildings for taxation purposes. And so fortunately, Quezon City, which is the largest city in the Greater Metro Manila area, it's a population of about 3 million people. The city government provided us with a copy of their database, which had about 200,000 records of building data. A lot of time was spent going through the data, looking for opportunities to actually match up the building types stored in there with the types from the UPDIs. But it wasn't enough just to accept those conversions and the data that resulted from that analysis. So we had to go back out to the field to try to collect more data. But this time we decided not to do a foot survey, and FEVOLX decided to deploy some cameras that they'd actually found in the local shopping centre to this effort. And so you can see on the right there, a very small camera, costs about $200. You can buy it from an electronics shop. Captures VGA quality video and GPS data at the same time. And so they installed in some of their vehicles 2 cameras, one looking left, one looking right, and then driving down the streets, capturing imagery as you go, driving very slowly. And then other vehicles became available. Yes, that's an ambulance with a camera attached to it. And so they took laptops and webcams out and essentially repeated the same capture process. So driving the streets slowly so that you get good quality imagery. So that's an example of Filipino ingenuity there for you. So spent several days in the field driving the streets in certain selected areas, and then going back to the office, and then we conducted an activity with engineers to review that footage and try to enhance the statistics about the building types in the different land uses that were observed. So much easier to do that than to go around on foot. So, as I mentioned earlier in the process, the building geometry model gave us the floor area sums for each of those polygons, but we needed a way to sensibly distribute the building statistics so that we weren't doing things like saying there's a super high-rise wooden building in this area. So we had to make some adjustments and develop the process around that. One of the last tasks was to try to distribute population through the project area. And we needed to think about the difference between the formally settled areas where people live in houses, condominiums, townhouses, etc., and those people living in informal settlements, those opportunistic settlement areas. So we'd actually map the difference between the two in the land use mapping, but then we needed a way to actually sensibly distribute the population accordingly. At the time that we did this work, the best available population data was just a barangay level population, but we used some analysis of another study to try to then find out, well, in those barangays in that city, what's the split between formal and informal settlements, and then distribute population accordingly. And then the result of the distribution is there on the right. So at the very end, we added back into the data an attribute about the local government unit and the barangay that could then be used for aggregating risk analysis results in later steps. So the result was this polygon data set, 85,000 polygons or thereabouts, each containing the attributes that you see there. The process was finished by preparing some metadata and product descriptions and then passing it over to the risk analysis teams, who then use that in their method to then calculate building damage, economic loss, and in some cases casualties from earthquake, tropical cyclone, severe wind and flooding. And so the results of that analysis were aggregated up to the barangay level and then up to the city level, and the results were put onto maps and put into reports and then handed over to local governments and other interested parties. And it's interesting because the handover of that information came 2 days after a very large earthquake in the Philippines, and so the event itself actually generated a lot of interest from the local media. Some of the other work that we did was to try to characterise the potentially wind-sensitive structures, and so looking at putting some geometric properties of those after locating them. And so there was some work to use existing aerial imagery plus some other data that the National Mapping and Resource Information Authority had available. And this was used to contribute to the risk analysis for severe wind. So this exposure work also yielded several useful outputs that hadn't been envisaged earlier. The local governments really saw the value of the land use mapping and were very excited to be able to get access to that so that they could take it and keep it updated themselves. The building geometry model also contained some intermediate outputs that would be useful for visualising things like the building density across the Metro Manila area, but also how buildings would cast shadows because of their height and the relationship of their height with the ground. So this is useful for other visualisation, sticking into maps, talking around with people about the complexity of the environment. And so we saw earlier how we were able to define the extent of vegetation areas, and that work was then also used to define the height of vegetation in different areas, and that input was included in the severe wind hazard modelling. And the slope of the ground right across the Metro Manila area was also used in the earthquake hazard modelling to try to understand how ground shaking varies with slope. So during the second half of the project, discussions were held on the crafting of a much larger disaster risk reduction program that would involve Geoscience Australia, later to be known as SAFER, or Safe and Resilient Filipinos. There was a need to bridge the GMMA RAP and the SAFER program, and so we embarked on a program called the Philippines Bridging Program. And for the exposure work, this gave us an opportunity to actually review the work that we've done in GMMA, implement some improvements, and discuss how exposure data has policy linkages to decision making. So the first thing that we did there was to conduct a review, solicit responses from both the chefs and the consumers of the exposure information, held some workshops to talk about these things, and we produced some recommendations for improving and enhancing processes, which we were then able to actually implement in the next short phase. One of the new opportunities that we had in this second phase of work was the availability of census data from 2010, and a much richer data set than we had available in the first part. So we're able to produce tables with combinations of building type, building material, population type, tenure type, etc., which enable us to greatly improve the way that we characterise the residential building stock. And a lot of work was then also done to industrialise the processes that we developed earlier, which were largely manual, and we created a series of toolboxes for our partners to then use going forward. Made some enhancements to the building geometry model application, and we worked very, very closely with one local government unit to enhance their exposure information. Also did some work to enhance the way that we characterise the potentially wind-sensitive structures with some new data that the National Mapping Agency had acquired. And finally, we conducted a very large workshop focused on looking at a framework for how we could develop national exposure information for the whole of the Philippines, with an aim of making sure that the national governments who needed to make decisions on disasters weren't faced with gaps in knowledge on exposure, which is really important in a time of crisis where you really can't afford to have gaps in the data. So conducted a workshop and solicited a whole lot of responses from the potential producers of the data, but also the end users. And sadly, due to budget pressures, the program came to an end just as that framework was being completed. So that program concluded in September 2015, almost 1 year to the day since our last mission to Manila on this work. So what might have come next for the work? As I mentioned, national exposure data, but also further improvements to the data in the Metro Manila area, particularly focused on improving the business, industry and critical facility data, infrastructure, and looking at the variation in the population throughout the day. So the population distribution that was done earlier was just the night time population. But of course disasters don't just happen at night time, so we need to understand where people are during the day potentially. So our primary purpose for this development assistance was to build capacity by learning through doing. But that didn't actually mean that we had all of the answers right from the very beginning. So this was our scenario right at the start. This was our challenge. And we had to work through all of these and find our way. And our Filipino colleagues often talked about the cooking analogy. One of the things they used to say was, we don't want too many cooks spoiling the broth. So it was important to make sure that we weren't having too many people in the kitchen making it difficult to actually achieve results. And on the Geoscience Australia part, we couldn't go around the kitchen behaving like Gordon Ramsay and barking instructions and providing critique in that way. So we're almost out of time, but I'll just quickly go through what does success look like for us. Well, things like when the penny drops or when the peso drops, so those sparks of innovation and ideas, when they're realised, seeing that realisation in our partners was very rewarding. Our partners have mainstreamed the language of exposure, and they use that very effectively when they're communicating with their government partners, and they're asking a lot of the right questions when they're engaging with them to solicit their participation on the exposure information development. There's now a less reliance on field data collection, but field data collection is still useful in some cases. Our partners are now passing on the methods that they learnt through this process to others who want to also have a go at exposure information development. And so there's been a huge uptake of tools, both proprietary and open source, amongst our partners to actually do this work. And there's a very strong interest in making the process easier and much more accessible through automation, adaptation of existing tools, uptake of new tools, applying new data sets, and adding more value to the exposure information. So what are the main takeaways for us? Pardon the pun. Engagement and influence is really important. You can't actually do a lot of this work without buy-in from the right people. Administrative data has a lot of uses beyond what it was intended for, and recognising those opportunities is a bit of a skill. Data integration is much easier when ingredients are free. You know, when we say free, what do we mean? Free as in beer or free as in speech? It's actually much easier to say open. So openly available data as the ingredients for doing this work. Foundation technical knowledge is absolutely vital for the chefs, and foundation geographic and statistical information is also invaluable. And so the producers of that geographic and statistical information, this sort of work really highlights the importance of their contribution. And finally, it's not possible to ever have the perfect exposure database, but lives depend on that lifeline of information to decision makers. And so trying to keep that data maintained and relevant going forward is a challenge, but it's a challenge worth taking up. So once again, just like to acknowledge the many people who were involved in this work. If I was to try and name them individually, we'd be here for another hour. But all of these people had a key input into the success of this work. And now it's time to eat. Thanks very much.